the zeros that we have found up to this point in section 4.3 have been rational zeros. That is, all of the zeros could be written as fractions. However, we are aware that there are some less user-friendly zeros called irrational zeros. So in section 4.3.3, we'll examine, once we find all the easy ones, how do we find those irrational zeros? Sometimes the quadratic formula will be necessary to assist us in finding these irrational zeros. Example 3, our problem is the same. Find all the zeros of the polynomial function. So this time we're not factoring, we're just looking at finding the zeros. Remember, the first step here is to graph our function. As we type this in, how many zeros are we looking for? Max. We are looking for a maximum of 3 zeros, a maximum of 3 x-intercepts, because we are dealing with a degree 3 polynomial. So looking at our graph, it appears to cross the x-axis 3 distinct times, so we can expect 3 zeros each with multiplicity of 1. Now, the leftmost and the rightmost x-intercepts are at spaces between those tick marks. So I'm going to start with an integer. Notice the graph crosses at x equals 3. I'm going to divide that out first to make it a little bit easier. All right, so our synthetic division process is set up. As we run through the numbers here, clearly, we have verified that x equals 3 is one of the zeros. Now, to think about this problem, if we think in terms of factorization, if x equals 3 is a 0, then x minus 3 is one of the factors. The other factor that would correspond to this one lives down here. The coefficients are 1, 3, and negative 7. Remember, we started with degree 3, so this is now degree 2. So the remaining factor is x squared minus 3x minus 7. Now, using what you know about traditional factoring, if I were to break this down into 2 factors, I would discover there are no 2 factors of 7 with a difference of 3. So this is not factorable. What that means is any attempt that I make at guessing the fraction values where this graph crosses the x-axis will be futile. They are not actually rational numbers. So what we're going to do to find the 2 zeros that are encoded by this remaining factor, notice 2 zeros are encoded here, I'm going to apply the quadratic formula. So just looking at this part, we're going to apply the quadratic formula to this part. You can think about it as solving this quadratic equation equal to 0. So we have negative b, notice b is negative 3 in this case, plus or minus the square root of b squared. Make sure you get b in parentheses there so the square comes out positive, minus 4 times a times c, all divided by 2a. As we work this out and simplify, our discriminant, or the guy that lives under the radical, the radicand, looks like under there we have 9 plus 28, which would give us 37, all divided by 2. So those are irrational numbers. Square root of 37 can't be simplified any further. And if I separated it into 2 distinct fractions, I wouldn't be able to reduce it. So those are the 2 irrational zeros that were encoded by our quadratic up here. So these are the other 2 irrational zeros. So our list of zeros will include the nice, neat rational number 3, as well as our irrational solutions, 3 minus the square root of 37 over 2, and 3 plus the square root of 37 over 2. Okay, let's try that again. The next example, we have f of x equals 2x cubed minus 10x. This one I'm not actually going to use my calculator on because I notice there is a greatest common factor between the two terms. So when I set this equal to 0, I can solve by factoring out the GCF, which is 2x. Factoring out 2x, this leaves behind x squared minus 5. Now, I have two factors. Remember, we are expecting 3 zeros. This one does not factor in a traditional way. So what we're going to do is at this point, let's go ahead and set each factor equal to 0, solve for x, including this quadratic factor. Notice when I set that equal to 0, it's pretty obvious that I can solve that very easily with the square root property. So add 5 to both sides, then take the square root of both sides. Whoops. Then notice when we take the square root of both sides, that's where we get our other two answers, positive and negative square root of 5. So these two are irrational solutions. Altogether, we have 3 zeros. Each 0 has multiplicity 1. They are 0 and negative square root of 5 and positive square root of 5. So in each of these examples, we started out on the first one with our traditional synthetic division process and reduced it down to a quadratic that in this case, on example A, would not factor, so we applied the quadratic formula, and that's how we came up with our other two remaining irrational zeros. On example B, we simply factored out the greatest common factor, and from the remaining quadratic factor, by setting it equal to 0, we were able to use the square root property, and that's what yielded the other two irrational zeros. Hope that was helpful. We will see you in the next video.